Anyway, thank you so much to the organizers for inviting me to talk to you all today. I'm really excited to give some my perspective on how humans and machines learn to learn. Now, another term for learning to learn is meta-learning, which you might have heard. And if you have heard of meta-learning, there are a lot of definitions that are associated with it. So for the purpose of my talk, it's really important for me to, I think, establish what I believe it to be, which is this process whereby priors learned from previous experience helps to inform faster learning and better decisions in the future. And in order to properly understand this definition, we need to first take a step back and define what learning is. And at the broadest level, you can think of this as being a process whereby you're taking some raw data and you're converting it into more useful representations. So what this means is, maybe in the case of supervised learning, you can think of labels to classify images, or reduced dimensional representation of the data to help it be more interpretable. Or in my favorite domain, reinforcement learning, you can think of it as maybe a policy that you can implement. And the way that we turn that data into this representation is what we call learning. There are many ways to do that and many components to this learning process. So typically you can have some kind of a model that represents your data, such as maybe regression or decision trees, k-means, clustering, what have you. And you also have a kind of an optimization process or method, and that allows you to update your weights or parameters theta of that model. Now, for every aspect of this learning process, you can actually meta-learn that process, and what that does is it helps to speed up that learning process itself. So meta-learning is essentially this process of applying learning to this entire process such that it's proceeding faster with each additional batch of data. And it's doing that by adjusting the parameters that determine how these representations are mapped. Now, the distinction between normal learning and meta-learning is this emphasis on trying to do better on new data. So learning faster with each additional data sample, as opposed to, you have some fixed data set and you're just trying to do the best you can on that. Meta-learning focuses on new data that's coming in. Note here that there are actually two time scales of learning. We have this faster inner one, which is doing this mapping, and a slower outer one that's adjusting this inner learning loop. And so this will be important later on. Now, here are just a few examples of what meta-learning looks like in ML and AI right now. They come in several flavors. So you can have optimization or gradient-based meta-learning. So the most popular example you might have heard of is model agnostic meta-learning, or MAML. You can also have non-parametric methods like matching networks, prototypical networks, and also black box methods that use LSTMs. So there's a lot of other possibilities, but I just wanted to give you a few examples of them here. And it's an actively growing field, but my favorite and the one that I'm going to focus on in this talk is black box, or also called memory-based meta-learning. And it's memory-based because it's typically using an LSTM or some kind of a recurrent neural network to implement that inner loop of learning. And so you don't really need to know the details of what an LSTM is, just to know that it's essentially able to integrate over past history of observations. So to make this a bit more concrete, let me take this previous diagram and redraw it in a slightly different way. So I'm just going to make it spread it out, and now we can look at it as being a more continuous version of training. So where we're constantly updating this recurrent representation of data that's coming in, and also how these parameters are determining how we encode our input. And this is more in line with how an organism, of course, learns in a real environment, which is by being in constant interaction with that environment, learning in a continual fashion, being able to change the states of the environment and so forth. And this is, of course, the case in reinforcement learning, where the agent is tasked with learning the best actions to take in an interactive environment in order to get the highest expected reward or total reward. And the outputs are, of course, then some policy or action sequence that you're then optimizing to try and get that highest reward. And of course, you'll then use an LSTM or some kind of recurrent architecture to be able to integrate over your past history of experience. And this brings me to the kind of meta learning that I primarily work with, which has reinforcement learning in both the inner and outer loop, which is called meta reinforcement learning. So you can see here that you have this inner loop of RL where you have an agent that's taking actions in an environment, and then it's getting back observations and reward, and it's able to integrate all of that using an LSTM, from which you're also being able to output a policy. And so this LSTM or an RNN is parameterized by learned weights theta. And of course, you can adjust those weights theta using this slower outer loop of learning. So typically, what I use is, for instance, policy gradient methods, or you can use any kind of like deep RL methods that you like. Now, importantly, this is training over a distribution of environments. So I mentioned before it was important to think about a distribution and not just a single, set of tasks. So we're essentially trying to now be able to optimize over this entire distribution because we want to be able to learn faster in this inner loop. And so we randomly sample from this distribution every episode. Now, to give a demonstration of what this system can do, I'm introducing here one of the earliest studies done in learning to learn, actually all the way back in 1949 by Harry Harlow. What he did was he took monkeys and he trained them to select from one of two objects placed in front of them, and one of which is always rewarding and the other is not. And then for 6 trials, he'll keep representing these same two objects with random left-right placements. And the monkey has to continue selecting the rewarding object. And after 6 new trials, he would present then 2 new objects that the monkey had never seen before, and it would then have to select again to get reward. Now, at the beginning of training, you can see that the monkey is operating at, fairly close to chance. So this lower line here. And then towards the end of training, it's now essentially learned this one-shot learning policy of where on trial 2, it's able to achieve almost 100% accuracy. So we implemented a version of this task for our agents. For practical reasons, we had to change it slightly so that instead of picking up an object using some sort of actuator or something, it's actually selecting between one of 2 images on a virtual screen by moving swiveling its viewport left to right, and it's learning entirely from pixels here. So this is essentially the agent after training performing this task. So it's being presented with entirely new ImageNet images every 6 trials. And we're seeing the policy here that's implemented by this inner loop of learning. So we've actually already just frozen the weights of that RNN. Those are not updating. And yet it's still able to perform essentially one-shot learning and all entirely from pixels. And you can see the agent's performance on the right here and see that it's very similar to what the animals were doing, where early in training, that lower line, it's pretty much a chance throughout the course of the episode of 6 trials. And then towards the end, you see that familiar pattern of one-shot learning, where it's able to sort of on trial 2 get 100% accuracy. Now, note that we didn't have to implement any sort of special architecture to get this behavior. This arises naturally out of the fact that that we have this memory that's integrating past rewards and observations, and we're training on this distribution of structured related tasks. Now, that was a very stereotypical example of learning to learn that was taken from the field of cognitive science. But if we think about it, this is actually, this type of one-shot learning is actually quite common in nature and in everyday life. So in general, the priors learned from your previous experiences help you to learn faster or make better decisions in the future. So the next time I'm encountered with a similar problem, I usually do much better with it and am able to learn much faster from it. In a recent review article, I actually proposed that meta-learning exists anytime there are multiple nested scales of learning, and that in nature there are just naturally many nested scales. Now, at the base, we have learning of highly invariant priors and the deep structure, just by virtue of the fact that we're existing in some consistent universe. And so these things that we're learning are something like universal physics, motor primitives, and this is learned via slow learning processes like evolution. And that in turn forms the basis and the priors for faster learning that can be done on a faster time scale, like within a single lifetime, for learning skills like navigation, learning specific languages, and so forth. And then that in turn forms the basis for learning on an even faster time scale, such as things that you can learn in a single day, like learning to play a new game, or to be able to navigate to a specific location. Now, there's actually a spectrum across which organisms learn at a combination of faster and slower scales, depending on how sophisticated their brains are. So humans, of course, have much more sophisticated brains. We're much slower to mature. We have longer developmental periods. And that translates into a higher capacity for fast adaptation within lifetime learning. So we can do more of this meta learning. Whereas insects, for instance, are operating on a much more innate instinctual level, and they have a smaller repertoire of behaviors, but they're very, very fast to mature. And this nicely maps on to two types of learning that we tend to study in neuroscience, which are innate behaviors, so those which are presumably evolved or pre-specified from birth, and those that are learned. So really nice example of innate processes that are studied is place cells, which has come up a couple times today already, most notably in Kim's talk. And so these are neurons in the hippocampus that seem to only fire in a specific location in a room. So that allows you to form a map of where you are and orient yourself in space. Another example is our propensity to form language. Now, learned behaviors that arise on top of these allow for fast learning and adaptation on much shorter timescales. So, for example, if learning where a specific place is in a certain room, or forming specific item context associations, relies on the fact that I have these place cells, or like these propensities to form place cells and grid cells. Or for instance, learning that bonjour is hello in French. So I already had to have some kind of propensity for learning language. And we can see this also happening on much faster timescales, where both forms of learning are within a single lifetime. Schema learning is one example of this. So schema learning is where the observation that knowledge is more easily acquired and retained if you have a pre-existing framework that already exists on which to scaffold that knowledge. So an example of this in everyday life is, for instance, if you're trying to study for a test, you probably find it a lot easier to remember a lot of facts if you have a kind of scaffold to be able to hang all those facts on, and if all those facts are congruent with each other and form a coherent narrative, as opposed to if they're just arbitrary facts, then it's a lot harder to remember. So this paper here that I've highlighted was one of the first investigations that actually looked at the neural correlates of schema formation from Rich Morris's lab, and essentially showed that while schema learning itself can be quite slow and mediated by hippocampal neocortical processes of consolidation, the learning of those individual knowledge that scaffolds onto those schemas actually can be a lot faster and can become independent of the hippocampus in, for instance, a matter of days. And this relates to an important point I want to make about meta-learning, which has to do with the no free lunch theorem. No free lunch theorem, if you've heard of it, is of course that the fact that the postulate that no one algorithm will work better than any other when you're averaging over all possible tasks. And the implication for meta-learning is that, whereas meta-learning stipulates that, inductive biases can help with faster learning, it will only help if you have structure that is already in your task distribution or in your environments. So if you can make assumptions about the kind of problems that you will be encountered. So to put another way, you cannot just meta-learn given an arbitrary distribution of tasks. You can't just throw more tasks at your agent and imagine and expect it to eventually learn the way that, for instance, a human does. Okay, and the kinds of things and the kinds of structure that you meta-learn depends on your task distribution and what kind of structures in your tasks. So for instance, it makes a difference if you train on all Atari games versus the real world. And the real world actually, I think, is quite special because it has a lot of internally consistent structure. This is why I'm so optimistic about meta-learning and why it can be, I think it can be useful in a lot of cases, because the kind of tasks that humans are most interested in are the ones that exist in the real world and naturally have structure built in. And meta-learning is designed to learn and capture that structure. So going back to memory-based meta-RL, we can ask if this kind of structure shows up in the representations that agents learn. And the reason we can do that is that recall that one important feature of this framework is that it's implementing the inner loop of learning via the hidden states of an RNN. And neural activity, we know, is a function of connectivity, and in the brain, brain connectivity is highly recurrent, and it's constantly integrating new input. And so the hidden state of an RNN can actually be thought of as a pretty good approximation of what's happening within at least recurrent systems in the brain, especially for training them in the right way. So this was something that we looked at in a paper that was published in 2018, where we found that the hidden states of these recurrent meta-RL agents can in fact very well capture the neural activity patterns taken from experiments with animals. So we implemented a series of tasks taken from the neuroscientific literature, and we analyzed the activations of these agents in a similar way that that the activations were that neuroactivity was analyzed in animals, and we found that they really nicely corresponded in a lot of ways. I don't really have time to go into the details of these, but the overall highlight is that we're able to see some striking similarities in both the behavioral characteristics as well as the neuroactivation patterns between these deep RL agents that were trained on these tasks and the animals that were performing these tasks, implicating that the prefrontal neocortical system might be implementing some kind of a meta reinforcement learning system as we envisioned it in this paper. But so all of these tasks that I've talked about, or that we actually mentioned in this particular paper, are fairly simple. So they're essentially just bandits, and bandits are really nice in that they offer great accessibility and transparency. You can define sort of optimal comparisons. You can define, you know exactly what a perfect agent is supposed to achieve and what a random agent is supposed to achieve. And the tasks that are used in neuroscience are a little bit more complicated than bandit tasks, but not by much. And that's because the main point of these tasks is to be able to get understanding into animal behaviors and to be able to pinpoint mechanisms of function. And so, at the other end of the spectrum, you have these very complicated environments that involve detailed exploration, complex action spaces, the kinds of games that humans play, like Final Fantasy or Atari. But these environments have, on the other hand, very low accessibility, meaning that they're so complex that you can't really define any kind of cognitive models of behavior or try to calculate an analytical ideal. So in this way, it's very difficult to interpret agents' actions or to try to get any insight into their understanding of their environment. So they either just can solve it or they don't, and you don't really quite know why. And then, of course, you have the most complex environment of all, which is the real world. But you can see that there's this kind of hole that exists, this gap, where we don't really have a lot of environments that are both easily, accessible and amenable to interpretation, and also at the same time has enough challenging complexity that it requires really interesting cognitive functions like smart exploration or learning how to plan sequentially. So that was the point of us introducing this new meta reinforcement learning benchmark called Alchemy. This is a game in which you're trying to transform various stones into highly valued quote unquote gold stones by dipping them into various potions. You can kind of see it in action here. From episode to episode, there are elements which both vary and remain consistent, which is important. So things like what the gold stone looks like or the effects of potions are varied from task to task, allowing for meta learning to occur, but you also have a deep latent structure that requires within a single episode for you to perform experimentation and to do exploration. Here on the right, you can see some examples of latent structures that we call chemistries that can be sampled every episode. So I don't have the time to get into the details of what they are, but suffice it to say, that like these structures are latent because they're not directly observable by the agents. The agent is only seeing things like what you can see on the right here. You can only see the physical features of the stones and the potions, and what the potions are doing to the stones. But those features and those transformations are related in a hidden way with this latent structure. And it's only through experimentation and inference that you're able to learn what the underlying rules of stone transformation are in that given episode. And it's this structure that allows us to define interpretable, useful models of behavior. And this allows us to gain insight into not only what the agents are doing, but also what they're understanding or not understanding. In this paper that we actually just released this year, we provide an example of this kind of analysis showing that some powerful deep RL agents that are able to solve a lot of other tasks like Atari or DM Lab, nevertheless not able to perform at a really high level. So we're able to define these Bayes optimal ideal observer reference agents, which you can see here on this graph, denoted by the dashed line at the top. And you see that the agents are performing much closer to what we call a random heuristic reference agent. Note that we're only able to define these Bayes optimal and other kinds of reference agents because of this deep underlying structure of Alchemy. And by comparing to these reference agents, which have built in specific kinds of knowledge, we can then make inferences about what these agents know or don't know. And we can also analyze their behavior in more detailed ways by looking at, for instance, here we show that the ideal observer reference agent uses far more potions in early trials as opposed to later trials. And that's reflecting the fact that it's getting a lot of information in the beginning of the episode, and then it's using that information in later episodes. So it doesn't need to do as much exploration in later episodes, because every time you use a potion, it's essentially you're getting information. But the deep RL agents are essentially not doing that at all. They're using the same amount of potions throughout. So this is indicating a failure of meta learning in this aspect of otherwise really powerful deep RL agents. So there's a lot of other kinds of analyses that we can do with these. I'm not going to get into them, but good news is that we've open sourced this. We provided it as a resource to the community, so anybody can apply their own agents and check it out. And I am now, I think, really out of time, so I'm going to just wrap up and thank all my colleagues at DeepMind and all of you for your attention.